Welcome to the Blood Vessels PowerPoint. The majority of this PowerPoint is going to be a review of what you learned in anatomy. There will be some new facts and a math equation that I'm going to need you to memorize, but I will point that out when we get there. So we'll start just by touching on veins, and then we'll move on to capillaries, and it's at capillaries where we're really going to look at blood flow in and out of the tissues. So at the veins, veins will be collecting the blood from the capillaries, and they'll be returning the blood to the heart. And because there's no pump on the veins, it's the pressure in the veins that's generated from the skeletal muscle around the veins, as well as from that initial pump of the heart, that's going to propel the blood back up against gravity to the heart. Now, the veins have a larger diameter than arteries, which means there's lower pressure in them. They also have thinner walls because they're carrying blood that is lower pressure. So with that being said, again, there are ways to pump that blood back up the veins. One of those is going to be the skeletal muscle contractions that actually pushes on the veins, propelling that blood upwards. It also naturally still has pressure that was provided to it by the contraction of the heart, but we also have these valves inside the veins. These are backflow valves. They prevent blood from falling back down and pooling in the lower extremities. So the movement of blood back up the veins is essential for getting that blood volume back up to the heart, and it's done because of the valves as well as the skeletal muscle contractions. Now, in terms of regulating blood flow as a whole in the cardiovascular system, you can control blood flow by vasoconstriction and vasodilation. If you're able to constrict blood vessels, that essentially increases blood pressure within that blood vessel, and it can also restrict blood flow to that area. So we'll look a little bit into the effects of vasoconstriction and dilation. Then you have capillary blood flow. This is the blood flow specifically through the capillaries. So if you recall, blood gets pumped out of the heart into the arteries, through the arterioles, then into the capillaries. However, sometimes there are situations where you need to provide certain tissues with more blood than others. For example, if you're running away from a bear, blood is probably going to want to be detoured to your skeletal muscle, your brain, your heart, and your lungs. So you're going to want to open up what we call capillary sphincters in those areas in order to allow blood to enter into those tissues. At the same time, you're going to constrict capillary sphincters, taking blood to areas that you don't really need when a bear is chasing you, like the digestive system, the urinary system, and the reproductive system. So capillary sphincters are a big factor in what allows blood to enter into certain tissues or to be detoured away from those tissues. In addition to capillary sphincters, you have cardiac output. We'll talk about the equation of cardiac output, abbreviated CO, but the gist of it is that cardiac output is directly correlated with capillary blood flow. The more output you have from the heart, the more blood flow there's going to be to the capillaries. And then again, the cardiac output itself is controlled by blood pressure and resistance. This first point here, this first dash, will make a lot more sense when we cover the equation used to calculate blood flow and resistance in your body, and that's going to be in the next video. Now, once that blood actually gets into the capillary bed, there are 5 primary ways of diffusion in the capillaries. And again, we do focus on diffusion rather than any kind of active transport. And the first big way is going to be diffusion of water, ions, and small molecules. Now, these are all very tiny, and because they're so small and they're hydrophilic, that means they like water, they're going to have the ability to diffuse in between endothelial cells. Now, before I move on any further, I just want to remind everybody that capillary beds, let's kind of just draw a capillary here. They are a single cell layered thick, and if you recall from anatomy, it's simple squamous epithelium. And some capillary beds have little tiny holes in them called fenestrations. So let's draw our simple squamous epithelial cells. We got one there. We're going to draw a neighboring one right here. We're going to draw another one right here. And if you can tell, I'm not making them touch each other. And that's because there's little spaces between the simple squamous epithelial cells of capillary beds. And those spaces are called fenestrations. And these little fenestrations in the wall of the capillary bed are going to allow diffusion of solutes in and out. Now, fenestrations can also look like holes in the actual epithelial wall. So, with that being said, simple diffusion can take place, allowing solutes and nutrients to leave the capillary bed, going out into the tissues that need that nutrients. Other ions like sodium, potassium, calcium, and chloride, these guys that are charged can diffuse through the capillary walls as well, and sometimes they require channels. So if we have a channel present, it'll use the channel. Then you've got large water-soluble compounds. They are large, which means they're probably not going to get through these little tiny cracks. They're going to have to go through these holes we call fenestrations. And again, the fenestrations, which labeled here, they're labeled here, they are all those holes that are found in the actual cells of the capillary. Number 4 talks about lipids and other components that are hydrophilic. That means they like fat-based soluble compounds. And with that, because they're fat-based or they're lipid-based, they're able to make their way through the actual membrane of the cell. Because remember, the cell membrane is also made of lipids, and like dissolves like. So if you are lipid-based, you're going to be able to diffuse through a membrane that's also lipid-based. The last one is plasma proteins. These guys are huge. Plasma proteins don't generally go in and out of capillaries. There are select places where you want plasma proteins to move in and out. And for that to actually occur, you need very large fenestrations. So these two little fenestrations that I drew are tiny, but there are some capillary beds that have big gaping holes in them called sinusoids. Sinusoids are a type of fenestration that are very large, and they're meant for the passage of large solutes like proteins or like red blood vessels. One place where you'll find sinusoid capillaries is going to be in the bone marrow and the spleen. Now, this slide, it seems like there's a lot of information on it in terms of down here at the capillary bed, but I'm going to break it down into pieces. So here you have a capillary bed, and we're going to assume that the blood is moving towards the right. So from artery towards the vein. These are 4 arrows that are going to indicate the movement of solutes in or out of the capillary bed. There are 4 different factors that control movement of solutes in and out of the capillary bed. Number 1 is going to be the capillary hydrostatic pressure. It's simply the pressure that's coming and pushing into the walls of the actual capillary. The pressure is so high here that it's going to start pushing solutes out. It's almost like a forceful push. So because of the high pressure, you're able to push out solutes from the blood out into the tissues over here. At the same time, you have a little bit of pressure pushing back in because, of course, the tissues themselves have fluid in them already, and that fluid's going to come and push back in. But if you look at the overall first part of the capillary, the net pressure is going to be a pressure pushing out. So in the first half of the capillary, what really controls the movement of solutes from blood out to the tissues is going to be the capillary hydrostatic pressure. Definitely overcomes the interstitial hydrostatic pressure. Then once you get to the end of the capillary, at this point pressure has kind of died down, and now we're really focusing on what's called osmotic force. You have osmotic force that's pushing out of the capillary and osmotic force pushing in. Notice that the one pushing in is a lot higher. So your net movement at the end of capillaries is going to be to move back into the actual capillary itself. Osmotic force is defined as the force of water moving towards areas of higher solute concentration. Now, because initially you moved out a lot of your fluid like water, a lot of what was left behind was larger substances like red blood cells and your big proteins. Those red blood cells and big proteins will stay in the capillary bed, and when they get to the end of the capillary bed, water from the tissue is going to say, ooh, look, there's big proteins in the capillary bed. There are large red blood cells in there. And because of osmosis, the water wants to move into the capillary bed, causing osmotic force to occur. So, with that being said, the beginning half of a capillary bed is controlled by pressure. The second half of the capillary bed is controlled by force. Now, why is the movement of fluid and solutes in and out of blood vessels so important? Well, it's similar to the reason why that movement is important in the lymphatic system. Now, although we don't cover a lot of lymphatic system in this course, we're going to touch a little bit on it here and discuss the importance of moving solutes, moving water, moving bacteria or pathogens in and out of these circulatory systems. So first and foremost, it's going to ensure that you have a constant plasma and interstitial fluid communication. There are communication molecules between plasma, between tissues, between glands, and simply between cells that require movement within blood. Number two, it helps to distribute things like hormones. As you already know, hormones travel through the blood. Nutrients travels, gases travel like oxygen and carbon dioxide. All of these are able to travel through blood. So it's almost like your freeway system in your body. You're also able to transport insoluble lipids and proteins that normally wouldn't be able to cross capillary walls. Number three is specific to the lymphatic system. So if you'd like next to it, just write lymphatic system here. And number four, it's able to flush bacterial toxins and chemicals through the immune system like lymph nodes. Number four is also a characteristic of the lymphatic system. So 1 and 2 are specifically for blood, 3 and 4 are specifically for lymphatic system functions. Now, controlling blood flow and pressure in the tissues. We kind of touched on it. We talked about cardiac output. We talked about capillary sphincters. But right now we're going to talk specifically about arteries and veins. How do you control pressure in your systemic circuit? That is the circuit of blood that travels everywhere else in your body but your lungs. Well, we have to get some terminology across first. Number one, systolic pressure. The maximum pressure in your blood vessels, and this is usually when the ventricles first contract. Then during ventricular relaxation, you have your diastolic pressure. This is the minimum pressure in your blood vessels. That doesn't mean it's zero. There's still pressure in there. It's just at a low amount. The pulse pressure is simply the difference between these two numbers here. Now, normal systolic pressure is around 120, and a normal diastolic pressure is around 80. So 120 over 80 is a pretty good number. If you're a little bit above, a little bit below, not a big deal. Here is that equation that I mentioned at the beginning of this PowerPoint. I need you to memorize the equation for mean arterial pressure, the average blood pressure through the arteries. It is equal to the diastolic pressure plus 1/3 of the pulse pressure. Now, this equation needs to be memorized, but you will not be needing a calculator on the next test. You will not be allowed to use a calculator on the next test, but the numbers I will give you will be very, very easy, and the pulse pressure will be divisible by 3, so you can easily multiply it by 1/3. I can give you an example of it now. Let's say you had a person who had a diastolic pressure of 90 and they had a pulse pressure of 60. Go ahead and calculate what the mean arterial pressure would be. The next two terms are hypertension and hypotension. Hypertension is going to be abnormally high blood pressure. This has to be above 140 over 90. Hypotension is abnormally low blood pressure, lower than 90 over 60. Now, regulatory mechanisms for cardiac output and blood pressure, there are three main ones. Now, these are just pretty umbrella um, mechanisms, nothing very specific here yet, but we will learn about specific mechanisms coming up soon. The first mechanism is called autoregulation. Now remember, auto means self. You're self-regulating. Autoregulation is done by the heart, and the heart has the ability to sense when blood pressure is too high or too low inside of it. Now, blood pressure and heart rate are inversely related in terms of the heart itself. If the heart senses that your blood pressure in the heart is too high, it will go ahead and lower the heart rate to control and regulate the cardiac output. Same thing if blood pressure is too low, the heart rate will increase. The neural mechanisms, this is going to be response in terms of the brain detecting any kind of changes in blood osmolarity. So the heart will respond to changes in blood osmolarity, and those changes are detected by the brain. So it's kind of cool. Inside of your brain, you have chemoreceptors. Now, if you remember, chemoreceptors bind chemicals. Solutes are chemicals. So if your salt concentration in your blood is very, very high, that means in your brain, you're going to have a lot more salt binding to chemoreceptors. The brain will sense the higher binding, and it will tell your body, hey, we have a lot more binding of salt to chemoreceptors. That must mean our blood osmolarity is high. You should probably drink some water. And it makes you feel thirsty. The more water you drink, the higher your blood volume goes. And the more blood volume you have, the higher the blood pressure is going to be as well. This whole mechanism, don't worry about memorizing this right now. I just said it to you to kind of give you this example, but this is going to be something we cover pretty in depth in the next two PowerPoints. But the gist of what this point is saying is that your brain does control your cardiac output, it can control your heart rate, and it can control things like thirst that will eventually control the blood pressure. The third one is the endocrine mechanism. The word endocrine always means hormones. So the endocrine mechanism will control long-term changes by secreting hormones. Hormones have the ability to change the function of organ systems, and one of the hormones that we're going to talk about is ANP, atrial natriuretic peptide. I will go over the function of it in a future PowerPoint in this section. But right now, just know that hormones can also control cardiac output. Now, there are a few basic vasodilators I'd like you to know about. Vasodilation is dilation of blood vessels. That means the blood vessel is getting larger. So vasodilation would look something like this. So instead of the blood vessel looking like this, the smooth vessel dilates, relaxes, and it opens up. Now imagine this. If you're going from a blood vessel this size to a blood vessel this size, would you imagine that if you had the same volume of fluid in here and then you dilated it, and that same volume of fluid was in here, would you imagine that the pressure would be higher in the constricted one or the dilated one? It would definitely be higher in the constricted one, much lower in the dilated one. What would cause blood vessels to vasodilate? Well, let's think about this again. If the blood vessel vasodilates, the pressure will lower in here. The blood flow is going to increase through this area because it's now less restricted, and it's going to cause more blood flow into tissues in these areas. So you'd want to vasodilate blood vessels to areas that you want more blood. Now, situations that would cause vasodilation is low oxygen concentrations. If your tissues feel that they're not getting enough oxygen, they're going to say, hey, vasodilate these blood vessels near us. Bring more blood in. We need more oxygen. Inversely, high concentration of CO2. If you have a lot of CO2 in an area, that usually means you don't have enough oxygen. Now, if carbon dioxide levels go up, that means your pH is going to go down. So let's write this ratio really quick. So high CO2 will cause low pH. Now, what do we know about low pH? Is low pH acidic or is it basic? It is acidic. So memorize this fact. The more carbon dioxide you have in an area, the more acidic that area is going to be. I will teach you this mechanism a little bit later. Just for right now, I just want you to memorize this fact. So a high CO2 will cause low pH. And as you know, low pH is the same thing as saying high proton concentration. So I put these in red because they're all kind of correlated with each other. And I'd like you to make connections between these 3 points. High potassium will also cause vasodilation. Inflammation from histamine will cause vasodilation, and high temperatures causes vasodilation. So all of these are going to cause vasodilation, increase blood flow to certain areas of your body. Now, kind of shifting along to talking about exercise. And really, I'm talking about exercise to talk about the availability of oxygen. During light exercise, you have pretty good oxygen flow in your body. During very heavy exercise, that oxygen content kind of goes down. So with that in mind, let's cover 3 effects of light exercise. So you're exercising the muscles are contracting, you do have a good amount of oxygen present. So you're going to have vasodilation to increase circulation. You're going to have more return of blood back up to your heart because you're contracting your veins. Remember, venous contraction will cause the propulsion of blood up towards the heart. And because more blood is getting up toward the heart, your cardiac output is going to rise. Again, cardiac output is the amount of blood that's pumped out of the heart per pump. Now, there's a term here that I really would love for you to know, and it's the Frank-Starling principle. As you pump more blood back up to the heart because you're contracting your muscles, that means a higher blood volume is getting back to your heart as well. Now imagine your heart, and we're just going to draw a generic heart like this. Imagine more blood getting into your heart. That heart is going to stretch out a little bit. And as the cardiac muscle stretches out, that cardiac muscle has receptors on it, specifically mechanoreceptors that measure stretch. The more the heart stretches out, the more the stretch receptors sense it, and that triggers the Frank-Starling principle. Go ahead and write this down. The increase of stretch, I'm just going to write an ST, the increase of stretch in the heart is going to trigger an increase contractility. And I'll just put CONT. So increased stretching of the heart is going to cause increased contractility of the heart. This word contractility means how hard the heart is pumping. So if the heart stretches out, it will sense that it has stretched out, and that more than likely means it's because there's more blood inside of it. And if there's more blood inside of it, the heart now needs to pump harder to pump the blood out. That pumping is called the contractility, the ability of the heart to contract. So the more blood that gets to the heart, the more the heart stretches. It senses the stretch to trigger an increased contractility to pump the blood harder out of the heart. That is the Frank-Starling principle, and it does have to do with stretch and contraction. Now, what if we took that light exercise and we made it heavy exercise? Heavy exercise now triggers your sympathetic nervous system. Now, when people think of sympathetic nervous system, they often think of a system where you are panicking, but that's not always the case. If you do heavy exercise, heavy cardio, a lot of weightlifting, that itself can trigger the sympathetic response, your fight or flight response. This is going to increase the cardiac output to the maximum level. It's going to now start detouring blood away from non-essential organs and redirecting it to essential organs like the muscles, the lungs, the heart. However, blood supply to the brain will remain unaffected because this is the organ that actually requires the most blood and glucose and sugars and ATPs out of anywhere else in your body. Now, we covered exercise, aka oxygen content and nervous system response. Let's now talk a little about hemorrhaging. Hemorrhaging is your body's loss of blood. So we'll talk about short-term hemorrhaging and long-term hemorrhaging. Really what I'm getting at here is blood volume. Short-term hemorrhaging means you're losing blood just for a short amount of time. The next slide is going to be long-term hemorrhaging, losing blood for a long amount of time. So 3 responses to short-term hemorrhaging. So your body realizes, hey, we're losing blood, but we'd rather not have our blood pressure drop. So what are 3 ways that we can maintain blood pressure regardless of that small amount of blood that we've lost? Well, increase cardiac output by increasing heart rate. So we're going to increase the heart rate. On top of that, cause peripheral vasoconstriction. Periphery means arms and legs. Vasoconstriction means you're constricting the blood vessels there. This is necessary because if you're losing blood, either internally or externally in your body, where are the essential places to make sure blood gets to? Well, not your arms and not your legs. Definitely your internal organs, like your brain, your lungs, and your heart. So if we vasoconstrict the blood vessels that are going to the periphery, we can instead detour that blood into the essential organ systems. In addition to that, you trigger the sympathetic nervous system. This is going to constrict your arteries to, again, cause an increase in something, and it's going to be BP this time. We're going to increase blood pressure. And we're also going to do some venoconstriction, constrict some veins. It's going to help blood move its way back up to the heart. And the last thing is the hormonal effects. There are certain hormones that can trigger and increase cardiac output, like these guys here, epinephrine and norepinephrine. You also have ADH, which is antidiuretic hormone, and angiotensin II. All of these guys are going to increase cardiac output and they're going to cause peripheral vasoconstriction. So you see that vasoconstriction is happening from both the hormonal effects and the carotid and aortic reflexes. These are 3 short-term responses to hemorrhaging. Then you have the long-term ones, like if you're bleeding for a long amount of time, so you have a lot of blood loss, what is your body going to do to make sure that your essential organs don't shut down and that you don't die? Well, number 1, it starts absorbing fluid from your tissues back into your blood vessels. Number 2, ADH and aldosterone, 2 hormones, are going to ensure that you don't lose more fluid in the kidneys. Remember, the kidneys filter the blood, pull out water, toxins, and salts to make urine. But if you have long-term hemorrhaging, these 2 hormones are going to make sure that the kidneys don't filter out that stuff. It's going to tell them to keep all of that in your blood. You're going to start feeling very thirsty, and you're going to start secreting a hormone called erythropoietin. This hormone stimulates red blood cell production. This is in hopes of making sure you have enough red blood cells to hold on to whatever oxygen you're able to get into the blood. Again, that oxygen is necessary so that your tissues don't start dying out. And the last few slides, I'm going to let you guys review on your own. I think it's just 3 slides. This is really just a review of arteries, veins, and heart. Make sure you read over them. It's the direction of blood flow that you should have learned in anatomy.